In this video, we are going to prove this fact about what we call P-series in mathematics. So in particular, the infinite series of this form converges if and only if the exponent we have here, P, is greater than 1. So this is an if and only if statement. We're going to prove both directions. Before I start with the forwards direction, let me just quickly talk through this series. So if you look at this, just be careful not to think it's a geometric series. At first glance, they look very similar. We have a base being exponentiated. In the geometric series, that base is fixed. That's our common ratio. And it's the exponent that changes as we create the series. In a P-series, the roles are reversed. So the base here is going to change and the exponent P is fixed. So in this result here, P in any situation would be a fixed number. And then you don't have to start at k equals 1, of course, but if you do, what happens when you start to expand the series? You get 1 over 1 to the p, that's just 1, plus a half to the p, or 1 over 2 to the p, that's the same number, plus 1 over 3 to the p, which you could also think of as 1/3 to the p, etc., etc. So p here is the same in all of these terms, and then notice what we are exponentiating is changing. So again, it's very common mistake I see is to mix this up with geometric series at first glance. Just keep them separate in your mind. This is an if and only if statement. Let's start with the forwards direction. We are going to prove that if this converges, then P is greater than 1 by showing the contrapositive. So what is the contrapositive? It would be not this implies not this. So in other words, P less than or equal to 1 implies divergence. Diverges like that. And this direction is quite short. It's going to fall right out of the hypothesis. So I'm not going to write out complete sentences or anything like that. I'm just going to do the computation. Okay, P is less than or equal to 1. K here is a positive number. It's running through the natural numbers. So if I take a positive number and I exponentiate it to P, that's going to be less than or equal to K to the 1. So in other words, we preserve the inequality here. And then let me cross divide. So we have 1 over K is less than or equal to 1 over K to the P. Notice here, both of these are positive, so we preserve the inequality again. But now look what's happening. We have that the terms in the series we are studying are individually greater than or equal to 1 over K. In other words, were I to write down any sum, let me just do capital N up here, 1 over K, this summation is less than or equal to replacing what we're adding up with 1 over K to the P. In other words, our series, our P series, is above a known divergent harmonic series. So by the ordinary comparison test, this diverges. All this tells us is that when P is less than or equal to 1, we have divergence. We don't yet know what will happen when P is greater than 1. So in a moment, I will come back, erase this, and we will see if we can prove the backwards direction. For the backwards direction, we want to fix this number P and show that the resulting P series will converge. That means that we're not going to compare it to the harmonic series this time, because if we did, ultimately this is less than the harmonic series, but being smaller than something divergent is not useful information. So you could start thinking like, well, what's a good series to compare it to? What's a famous series that we have a good handle on that we know to converge? And that is the geometric series. I'm not going to set this up as a direct comparison with the geometric series, but ultimately knowing how geometric series converge will come into this. So I will use the geometric series. It's just going to be not quite as direct of a comparison as in the forwards direction. All right, so let P be greater than 1. And the first thing I'm going to note is really just something that's true about any series that consists of positive terms. The sequence of partial sums is monotone increasing. So for what happened to this marker? Let me switch out to this one. For any index n, if I look at the n plus 1th partial sum and compare that to the nth partial sum, it's equal to 1 over n plus 1 to the p. Everything here is positive. That's greater than 0. So that tells me that the sequence of partial sums is monotone increasing. I'm just going to write this like that. All right, we have a sequence of partial sums, which is monotone increasing. Whenever you're working with sequences and you hear the word monotone, you also want to hear the word bounded. So that's going to be the trick here, is I want to create an upper bound for every possible partial sum. That would give me a bound for the entire sequence of partial sums. So now let's just let n be a natural number and choose. This is going to seem like it comes out of thin air, but it's because I worked it out on scrap paper. So choose m from the set of natural numbers, and just to make my general expression very valid, let's make m greater than or equal to 4, so that n is less than 2 to the m minus 1. The reason why I'm even passing to a new number is because I want to work with this partial sum. It turns out this partial sum has a very nice form. So I'm going to go up in size using monotonicity from this partial sum that we're actually interested in, just the nth random partial sum, to one that I can give a really nice expression for. So then s sub n is less than or equal to s sub 2 to the m minus 1. And that's just from monotonicity. And now I'm going to write this out. And as I do so, I'm going to drop in a bunch of unnecessary parentheses to create groups of terms. So the first term in this expansion, if we're starting from k equals 1, let's just assume that we are, is 1 plus, okay, here's an unnecessary parentheses, 1 over 2 to the p plus 1 over 3 to the p, close that off, plus, sorry, I'm going to be right behind the writing, but I'll step aside in a moment, 1 over 4 to the p plus 1 over 5 to the p plus 1 over 6 to the p plus 1 over 7 to the p. Close off that grouping. So here it's like I started at 2, and I went up until I was just before the next 2 power. Okay, so it's hard to see with just 2 groupings, but I have 2 and 3. And then here's a 2 power. I want to collect terms until I get to the next 2 power. We'll stop just before that. So 4, 5, 6, 7, because the next 2 power is 8. And then we imagine that we keep doing that until, let's see, what would our final 2 power look like? Well, this is the third partial sum. And notice it stops, let's see, this is s sub 3. And this one is s sub 7. So we are going up through this number. Okay, so we will have 1 over, let me write the result and then I'll step away so you can copy it down, and then I'll maybe tell you where these came from. 2 to the m minus 1 to the p. I claim that that's what the first number in the final grouping should look like. And then the next one, just to expand the pattern, would be 2 to the m minus 1 plus 1 to the p plus dot 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 plus. And then the last one for this 2 to the m minus 1 partial sum is that number, right? Because here s sub 7, it was 7, s sub 3, it was 3. Here it's going to be 1 over 2 to the m minus 1. All right, actually, before I step away, let me just justify this number. Notice this is 1 less than 2 to the m. It needs to start at the previous 2 power. Sorry, I left off to the p. It needs to start at the previous 2 power. So the next 2 power is 2 to the m. The previous one is 2 to the m minus 1. So that's where this came from. This is like a generalization of how I grouped these and these. And if you'd like, you can do the next grouping after this one, the next explicit grouping, which would start with 1 over 8 to the p and end with 1 over 15 to the p, because the next one is 16, and that should be s sub 15. All right, let me step aside so that you can look at this. We are, in our next maneuver, going to go up in size. So I have here a bunch of different denominators. What do I do to denominators when I want to go up in size? At this point in our real analysis course, it shouldn't surprise you that I want to go up in size, which means that I'm going to take a lot of these denominators and make them smaller. Because for positive fractions like these, a smaller denominator leads to a larger fraction. So in particular, for each of these groupings that we have, we are going to replace all of the terms in the grouping with the smallest possible denominator. So in other words, this 3 is going to go down to 2. The 5, 6, 7 will go down to the 4. And here, all of these will go down to this 2 to the m minus 1 to the p. I'm just going to fit probably one more line on here before I'm going to need to erase. So let's set this up, and then I'll give you an exercise. And in the interest of space as well, I'm going to kind of summarize what happens when we make that change at the same time. So if I take this 3 and knock it down to 2, that means I have two terms which are both 1 over 2 to the p. And then here we have four terms which are all 1 over 4 to the p when we make this adjustment and go up in size. So we have four terms that look like 1 over 4 to the p. And then however many other groupings we have, it depends on m. But maybe I haven't emphasized this enough. The fact that I have exactly groupings like this, I don't have any remainders, is because of the special form that we gave this partial sum. So 2 to the m minus 1, again, if you write s sub 3, s sub 7, s sub 15, s sub whatever this is, it fits into the same pattern of having this final cluster. Okay, how many terms do we have here? You can figure it out on the spot, or you can always say it's this number minus that number plus 1. We need to do accounting. So where did I stop minus where did I start, and then add 1 so that we add that back. So 2 to the m minus 1 minus 2 to the power m minus 1, add back to include the first term. Okay, so this is how many terms we have in this final cluster, and now they are all going to have the form of 2 to the m minus 1, all of that raised to the p. Okay, and I'm just about out of room. Let me give you an exercise, and we will come back in just a moment. Okay, well, for one thing, simplify this. That goes without saying. Here, we'll have the exact same kind of simplification. So start to make simplifications here. Additionally, I want you to take this 4 and rewrite it as 2 squared. So 4 to the p is the same thing as 2 squared to the p. And then notice we have 2 to the 1 to the p. Here we have 2 to the n minus 1 to the p. Again, this special 2 power that's emerging is because of the special form of the partial sum. So then I want you to write this maybe another time where you reverse the exponents here. This won't stay as p, these won't stay as p because you're going to do some simplification. But basically you have 2 to an exponent to an exponent. Reverse the order there. And that just comes from the fact that 2 to the a to the b is 2 to the ab, which is the same thing as 2 to the b to the a. So you can swap the ordering here once you've done your simplification. And when I come back in just a moment, we will see if you got the same thing I did. I'm going to have all of this erased and probably rewrite the ideal simple form right here. This is the expression that I wanted you to arrive at after doing full simplification and also reversing the order of the exponentiation in each denominator. So we have this leading 1, and then this expression here, 1 over 2 to the p minus 1, which, just to make it fit into a larger pattern, I've written as 1 over 2 to the p minus 1 to the first power. This is the upper bound for that first grouping, 1 over 2 to the p plus 1 over 3 to the p. Then this expression is the upper bound for the second grouping that had 4 terms. Notice here, let me just do a little bit of solution showing. So this was 2 squared to the p minus 1. So it's 4 to the p minus 1. 4 is 2 squared. And then I wanted you to flip the order here and write this as 2 to the p minus 1 squared. This expression, you might have just gotten to it through pattern recognition. We had 2 to the p minus 1 minus 1, no, 2 to the p, sorry, trying to work out of memory here. It was 2 to the p minus 1. This was the coefficient out front, and then we subtracted off of that 2 to the p minus 1, and then we added 1. Okay, that was how we counted up the number of terms in that grouping. Well, the 1's cancel, and if you didn't know what to do here, just factor 2 to the p minus 1 out, and you're left with 2 minus 1, which is 1. So really, this is just 2 to the p minus 1. That's how many terms we had in that final grouping. It simplifies with what was in the denominator, leaving us with this expression. And again, the more natural ordering from the work that we were doing was to have these exponents reversed, but I want you to write it like this. Now, why is this presentation better? Look at what's fixed and what's changing, perhaps relative to what was fixed and what was changing with the starting series. So if we look back at the P series, I wanted to emphasize that the exponent is fixed and the base is changing. And I said that's different from geometric series where the exponent is changing and the base is fixed. So the exponent is changing, the base is fixed. That's what we have here. So we have a constant base of 2 to the p minus 1. And then our exponents are really starting at 0 here, 0, 1, 2, all the way up through m minus 1. So I can say that this truncated sum here, this is just a finite sum, I can literally write it using, see, I've already got n here and k there, so let's switch to j. 0 to m minus 1, 1 over 2 to the p minus 1 to the j. So this finite sum is this. Okay, well, this is a finite sum. We're adding to it positive terms as we expand this. So I'm actually, in the interest of space, going to take this top bar here and replace this upper bound with infinity and go up in size. Now this is an infinite geometric series. We know what it converges to. If it converges, take a moment to verify that it does. We just need to check that this base, which is greater than 0, is less than 1. We have p is greater than 1. That means p minus 1 is greater than 0. So 2 to the p minus 1 is greater than 2 to the 0, which is 1. So then when we invert it, 1 over 2 to the p minus 1 is less than 1, 1 over 1. Sorry, it's got a little sloppy here, but this was greater than here. Okay, so this is a convergent geometric series, and we know what it adds up to. It's going to add up to first term divided by 1 minus the common ratio. You don't even really need to say explicitly what that is, so long as you know that this is a finite number, but let's go ahead and write it down. So the first term is actually here, it's 1 over 1 minus the common ratio, so that's 1 over 2 to the p minus 1. That's fine written like that, but if you want to, you can multiply top and bottom by 2 to the p minus 1 if you just want to make it look a little bit nicer. And we have 2 to the p minus 1 over 2 to the p minus 1 minus 1. All right. Now, this number, again, I don't actually really care what its value is. What it's doing is serving as an upper bound for every single partial sum in the sequence of partial sums. So notice here, n was arbitrary. I said pick an n, go up to a larger index, m, or actually it doesn't even have to be larger, but what we want to do is go up from this partial sum to this one. So we pick m so that 2 to the n minus 1 is larger than n. By monotonicity, we can say that the nth partial sum, which is random, is less than or equal to this one, which has a special form. We're able to turn this one with a special form into a quantity bounded above by this truncated geometric series, which we bound above by the entire geometric series, which equals a finite number. So this upper bound is an upper bound for the entire sequence of partial sums, which means that our sequence of partial sums is both monotone and now bounded. And that tells us that it converges by the monotone convergence theorem. I'm just going to write that here. Since the sequence of partial sums converges, so does the series. And we're done.